Field investigation and geological mapping are the backbone of tectonic geomorphology. They provide ground truth for remote sensing and reveal where and how the crust is deforming. We start at the regional scale. Investigators scan landscapes for geomorphic signals of active tectonics, fault scarps, linear valleys, offset rivers, and steep or anomalous stream gradients. Mountain front sinuosity and stream gradient indices help flag uplifted and faulted segments. Let's build a simple plan view map to see these ideas. High stream gradient segments and straight mountain fronts often cluster where uplift rates are high. Offset rivers across faults record cumulative slip. We can measure the offset distance directly in the field. Modern field mapping integrates classic tools with precise instruments. We combine topographic surveying, structural measurements, and stratigraphic logging with high-precision GPS and digital mapping. Drones and photogrammetry help in rugged or forested terrain. At detailed sites, we measure geomorphic markers to quantify deformation rates. For example, an offset river terrace across a fault can yield a slip rate when paired with the terrace age. Slip rate is simply offset distance divided by age. 24 meters divided by 8,000 years gives 3 millimeters per year. This is a typical calculation used worldwide to estimate fault slip rates. Another key field method is paleoseismology, trenching active faults to expose and date evidence of past earthquakes in young sediments. Let's sketch a trench wall, layered units cut by a fault with datable samples to constrain event timings. By dating layers and their disruption across the fault, we bracket earthquake times. Multiple events in a trench sequence allow recurrence estimates over millennia, crucial for seismic hazard. Case studies show how these methods work together. In the Himalaya, mapping the main frontal thrust scarp and uplifted terraces, paired with dating, yields uplift rates of roughly 1 to 5 millimeters per year and informs earthquake recurrence. In California's San Gabriel Mountains, anomalously high stream gradient indices coincide with rapid uplift. Along Slovenia's Sava Fault, a displaced alluvial fan shows 50 meters of offset in about 27,000 years, implying about 1.8 millimeters per year of slip. In the field, teams prepare geomorphic maps that classify landforms by age and origin, trace active faults, and measure offsets. Structural data, like bedding and fault plane orientations, reveal deformation style. Topographic surveying quantifies vertical and horizontal offsets with centimeter accuracy. All of these observations anchor our understanding of active tectonics. They calibrate remote sensing and models, and they feed directly into seismic hazard assessments and land use planning. Field mapping saves lives by identifying active faults and quantifying their behavior over time. Remember the simple recipe: measure a displacement, date the landform, and compute a rate. Thanks for exploring field investigation and geological mapping in tectonic geomorphology.